Okay, so in today's lecture, we'll pick up on this idea of looking at the explanatory variables that we put into the model. And so in the last couple lectures, we looked at the F-test, which could be asked, used to ask the question whether we can take certain, for example, test the hypothesis that we can remove certain explanatory variables from our model. And sort of related to that is that there can be other issues with the explanatory variables, in the sense that some of them might be redundant. Okay, so we're going to look at a related aspects. We're going to focus on the relationship between the explanatory variables themselves. And so today we're going to talk about what's known as multicollinearity. Okay, and so the basic idea is that this occurs when some of the explanatory variables are related amongst themselves. Okay, and so in particular, when some of those variables have a strong linear relationship with each other, then that can cause some potential issues if we fit the model with all the variables. Okay, so we're going to look at when that occurs and how to deal with it. Okay, so it occurs when some explanatory variables have a strong linear relationship amongst themselves. Okay. Amongst themselves. What we mean by this is we can express or close to being able to express one or more explanatory variables in terms of the other one. So for example, this might occur exactly. So for instance, let's say our explanatory variable, so I'm writing this as the vector for x3 in our matrix of the predictors. So for example, let's say x3 could be written as some combination. So let's call this like alpha 0 times, so the intercept plus some x1 and x2. Okay, so in this example, we could write the third explanatory variable as a linear combination of the others exactly. Okay, so this is a case where you have exact linear relationship. In fact, we have linear dependence between the columns of x in such a case. Okay, so in which case, so the columns of the x matrix, okay, the columns of x would be linearly dependent. Okay, and so this is something we touched on a little bit previously. So we have linear dependent columns in x, then we can't do the matrix inversion to get our estimates of beta. Okay, so that means this key matrix x transpose x does not have an inverse, and so we cannot calculate the estimates for the regression parameters. And logically, from thinking of using the x's to predict y, well, clearly, if you can write one of the predictors in terms of a linear combination of the others, then you don't need to have this variable in the model. Okay, so clearly there's no additional. Okay, then in practical terms, practically, there's no new information by including this variable x3 in the model, including x3 when x1 and x2 are already in the model. Okay, so that's as a practical matter, and so clearly in this case, then we would drop the linear dependence columns before carrying out our regression analysis. So this is exact linear dependence, but more frequently, we won't encounter this specific situation, but we might still have a case where the columns of x are almost linear dependent. And so that occurs when some of the x's have a close to correlation 1, for example, pairwise, or you can almost write one of the x's in terms of the others. Okay, so in the case of approximate linear dependence, or approximately, okay, so for example, x3 is close to being equal to a linear combination of the others. So in this situation, we can still fit the model. Okay, so x transpose x will be invertible because it's not exactly linearly dependent. Okay, so we can still estimate betas, but intuitively, of course, there's still not a whole lot of new information incorporated in the model when x3 is almost a combination of these other ones. Okay, so from a practical standpoint, we still don't gain a lot, and in fact, what we'll notice is in the estimates, you actually get much poorer estimates of the parameters when you have this sort of relationship among some of the x's. Okay, so in which case, so this is of course the more commonly encountered case in practice, because normally we won't purposely throw in things in the model that are linearly dependent. But for example, we measure a few variables that actually are very highly correlated, and so we'll encounter this when we fit the model. Okay, so the columns of x are close to being linearly dependent. Okay, and so what happens as a result is it causes the estimates to be poorly behaved. Okay, so I'm going to explain what I mean by that. So it causes the variances. Okay, so remember when we do the estimates. Okay, so we have we're going to use the variance of the estimators, okay, so with sigma plugged in, the estimate of sigma plugged in, to get our confidence intervals and to do hypothesis tests concerning our parameters. Okay, so these variance terms to be inflated. Okay, so the variances of the parameter estimates will be quite inflated, and we're going to see later as an example of what can happen in this situation numerically. And so inflated, that means the variance are going to look like. So when we do, for example, we do LM in R, and then we look at the summary of the LM outputs, we might notice that some of the predictors appear to be insignificant. Okay, and why would they appear to be insignificant? Well, because the estimated variance, Okay, so in other words, the standard error of the betas, okay, is quite large, and so therefore it looks like from the it could look like from the t statistic that those predictors actually are not significant. Okay, so which in turn can cause leads to so if the estimate of the variances are blown up, okay, and large, then because of multicollinearity, in turn leads to inaccurate, for example, inaccurate confidence intervals and conclusions and conclusions of hypothesis tests concerning the parameters. For the regression parameters. So in fact, one sign of multicollinearity is if, for example, we add some variables to the model, or we take some away, and we notice that the estimated variances, so the standard errors of our parameter estimates look like they change drastically, then that's a sign that some of these predictors are actually quite linearly related to each other. Okay, and turn leads to inaccurate confidence intervals and conclusions for hypothesis tests, and in practice, for example, the standard errors, when we fit the regression, when fitting the models, can change drastically when we add or remove variables. Adding or removing variables from the model. Okay, so that's the basic idea. So let me give you a couple of real life examples. So I don't know how many of you watch hockey. I mean, it's of course it's a pretty big deal in Canada, and when I was teaching in the States, I would use that as a I would talk about Canadian things, right? When I was in the U.S. and of course hockey was a stereotypical one of them. So suppose okay, so let me give you a quick example. So we know in hockey, so you have goals and assists. And that equals the points scored by a player. Okay, so say in the NHL. So for example, say you want to predict, let's say, a forward's salary. So for example, if we have these all three of these measurements, say for their performance last season, and of course maybe a whole bunch of other variables. Okay, so say we have this really big data matrix with a whole bunch of possible predictors of salary, and say if we just threw in all of these things, so we have, like, say x1 is the number of goals they scored, x2 is the number of assists, x3 is the number of points, and and so on. Okay, so we can have many other predictors. But as soon as I have all of these three, if I put them into the matrix of x's that I use to fit the model, then I'm going to run into multicollinearity because in this case x3 is equal to x1 plus x2. Okay, so for every player in my data set, well, clearly the column of x3 is always exactly equal to x1 and x plus x2, and so we would not be able to fit the model. Okay, so this would be so but x3 is equal to x1 plus x2, and so we have exact multicollinearity. Okay, so as an example of a practical situation where we might mistakenly throw in linearly dependent variables, and then we would get, and then if we try to do this in R, and we would get an error because the matrix x transpose x is not invertible because it has linearly dependent columns. Okay, and so that's one practical example. But often, as mentioned, near multicollinearity might occur simply because of the kind of variables we measure on the units that we're studying. And so over here, I have a picture of another famous creature in Florida called the python. Okay, and so in fact, the python is not a native to Florida. In fact, the pythons were mistakenly brought there. So this is the type of python we often see in Florida is the Burmese python. And what started out as people owning so-called exotic pets in their homes. So they bought these exotic snakes and had them as pets. And sometimes, and these snakes they eat a lot. They can grow pretty big. And so if you imagine people started letting them out because they didn't want to take care of them, and then all you need is one male and one female, and they will breed and multiply. And so now, many years later, Florida has this huge problem. You have these massive pythons eating up a lot of the what's originally part of the Everglades ecosystem. So it's a huge problem in terms of wildlife management in Florida. And so a few years ago, they collected some data on these pythons. So let me give you some of the variables. Okay, so here's example 1 and then example 2. So pythons, Burmese pythons in Florida. So this was a study from 2017, and they measured a bunch of things about. So they wanted to look at the health of these snakes. So the response is some variable associated with how fat these snakes were. Okay, so fat. I can't remember the unit. Let's just call it fat content. Okay, so as predictors for that, suppose we measured a bunch of things. So say x1 was say the mass of the python, and then x2 was say the overall length, and then x3 was the snout to vent length. Okay, and let's suppose for now there's these three variables. So So it turns out, well, actually, I mean, if you look conceptually, I mean, these are all measuring different things, but in fact, they're quite correlated. Okay, so clearly, like when the longer the snake is, usually the heavier it is, and so that might be expected to have a somewhat strong relationship. And then the relationship between these two measurements of length are also, in fact, highly correlated. So all of them are there. So they're not. There's not any exact linear relationship of these, but it turns out that x2 and x3 in particular. So x2 and x3 are highly correlated. Okay, so what that means is that if you including all the variables, in the regression would lead, so we can fit we were able to fit the regression because we don't have exact linear dependence, but it will lead to inflated variance estimates. So the standard errors in particular for the beta 2 and beta 3. Okay, so in this case, you have a pair of them that are highly correlated. So this study is we'll look at the specific data in R just in a little while. So I don't remember exactly where they got these 248 pythons from, but they were collected over a number of years. I suspect that some of them were collected from what has now become known as the annual Python challenge, which you might think refers to a programming contest, but in Florida it refers to giving citizens the opportunity to go out and catch these snakes, and people will get paid for turning in pythons to the government. They would be paid by it'd be stratified according to how long the snakes were, and so some people who had a lot of time in their hands and maybe some expertise at catching snakes participated. So this was one of the state's creative ways for doing wildlife management. Okay, so that gives you some practical situations of multicollinearity. So next thing to talk about is, well, how do we detect it, and then what do we do about it? Okay, so how to know what we have. Okay, so how to detect. Okay, so how to detect the problem? Okay, so let's look at two cases. So if exactly two of the variables are related, okay, so if two predictors are related, we can detect it a lot more easily because we can just do pairwise scatter plots and look at the correlation coefficients between the axes. Okay, so you can make a scatter plot. Okay, so scatter plot matrix. So that means we plot all pairs. So remember, scatter plot, we only plot two variables at a time. So when we say scatter plot matrix, it means plotting all pairs of scatter plots. Okay, so so what this means is all possible pairs of scatter plots between. So usually we plot the response and then all the predictors. Okay, so So I mean, we've already seen examples of scatter plots where we plot the response against, let's say, the first predictor, the response against the second predictor, and so on. But in the scatter plot matrix, we also make scatter plots of the predictors amongst themselves. So we also have a scatter plot of x1 with x2, x2 and x3, and so on, all the possible pairs. And so if for example some of the predictors have a strong relationship among that pair, then we will see approximate what looks like a linear relationship between predictors. So that will show up in the plot. We can also simply just calculate a correlation matrix between all the variables. Okay, so that's visually, so it's the visual way, and then we can also numerically calculate a correlation matrix. Okay, so again, so this is like all pairwise correlations. Okay, so I will show you in just a little bit how we would do this in R with a couple of examples. Okay, but what if the relationship is it's not just between two variables, but say like you have a close linear dependence between, let's say, x3 with a few variables like x1, x2, and x4. Well, in general, we will need to we might not be able to, that might not show up visually. So if we're looking at multicollinearity and want to detect it among more than two variables, then we need one way to do it in more generality is to calculate some statistics. Okay, so in particular, what we call variance inflation. So in general, for multicollinearity between more than two variables, we can look at, well, how much larger did the estimated variance get as a result of adding these predictors to the model. Okay, so we're going to define the variance inflation factor. Okay, so we'll call this the VIF. Okay, and we can calculate that for each of the predictors. Okay, so we define it intuitively like this. So the VIF for predictor, so this is predictor J. So we can calculate this for each predictor. So the variance inflation factor is defined as the ratio of variances. Okay, so the variance of beta j calculated in two ways. Okay, so so variance of beta hat j, that's the usual that's the usual estimate for the model with all of the variables. Okay, so and then on the bottom we calculate a reduced model with only predictor j. So I'll call this beta hat star. Okay, so let me label these. Okay, so this one on the top is based on fitting the regression with all of the predictors. So this is the estimate of beta j with all predictors in the model. And then this one on the bottom is this beta hat star is the estimate based on regression model with only the corresponding variable, so that'd be xj. So this one is the estimate of beta j based on regression with xj only. Okay, so that's what's called the variance inflation factor. So to calculate it, we fit two regressions. We fit the full model with everything, and we fit the model with just that predictor. So it can be shown that this ratio is always larger than 1. Okay, so the proof of this fact, and then we're gonna write this in a slightly more convenient form, requires quite a bit of linear algebra, so we won't go into that for our purposes. Okay, so this can be shown that the variance will get larger. Okay, so let's say this thing. So this can be proved. Okay, so this gives us intuition behind how how to measure just how much the variance grew by adding potentially correlated predictors to our model. Okay, so in practice, this is how we can another one way we can look at the calculation in terms of a familiar concept to us called R squared. Okay, so notice when we look at the correlation matrix, this gives us the sample correlations R, as we usually call it, between all pairs. Okay, so if we're just looking at pairs, then R squared, if we just have a simple linear regression, is simply the square of the correlation. And so it's the same generalization here. So for multicollinearity between more than two predictors, one way to measure this is to look at the R squared between in regressions of each x on all the other predictors. Okay, so let me explain exactly what I mean by that. Okay, so this can be viewed as follows. Okay, viewed in terms of R squared like this. Okay, so what we mean is, okay, so we're going to do this, fit a multiple linear regression so we're going to take one of the predictors, let's call it xj, in terms of the other predictors. Okay, so specifically, so we're going to treat xj as our response for this purpose. Okay, and then so basically we're fitting this a regression of this form. So we're going to do the usual things where so you have alpha 0 plus alpha 1 x xi1. Okay, so it's going to be based on everything except the jth one. So we will go up to j minus 1 x I j minus 1. Okay, and then we're going to skip this one because this is the one we're using as the response for this purpose. Okay, so plus j plus 1, and then the rest up to p. Okay, so this is what we mean. We take out the jth variable, and then we can fit a multiple linear regression on the remaining predictors. Okay, and so we can compute. So after we fit this, for example, using LM, we compute the R squared for this model. Okay, and let's call it R squared sub j. Okay. Okay, and so the intuition then is, remember, if R squared j is, for example, 1, then that means that xj is actually perfectly linearly dependent on the others. Okay, and so it will be exact multicollinearity. But in general, if R squared j is large, then that means we have something that's close to being multicollinear. Okay, so therefore, the intuition is that if R squared j is close to 1, we have that xj is strongly related linearly to the other predictors. To the other predictors. Okay, so close to being some linear combination of them. Okay, and so what we can use as a formula for VIF based on this concept is it can be shown that it can be shown that based on this R squared formulation, we can use this to calculate the VIF. Okay, and it's actually very simple. It's just 1 over 1 minus R squared j. Okay, so the linear algebra is a bit messy behind this proof, so we're going to omit it. But we can still look at this formula and see what the relationship between the variance inflation and the R squared in this regression of one predictor on the others. So in fact, this shows that, we know that this, based on this, looking at this formula, we know that the VIF is always at least equal to 1 because we know R squared is between 0 and 1 inclusive. Okay, so specifically, the larger R squared is, then the larger the VIF will be. So, for instance, as a practical rule of thumb, but what do we consider to be strong multicollinearity? So many books will recommend that if the VIF for any particular predictor j is greater than or equal to 10, so that be considered a quite strong multicollinearity. We have serious multicollinearity. So we look at these numbers. Well, what is what R squared j gives us this? Well, that means if this is greater than 10, then that means you have 0.1 on the bottom, which means R squared j would be at least 0.9. Okay, so this is equivalent. So this is R squared j is at least 0.9. Okay, and so this gives us a rule that can be used in practice to help eliminate multicollinear variables from our potential regression model and detect these problems and remove any associated variables. Okay, so as a procedure, practically speaking, so we could recommend this as a way to solve the multicollinearity is we can remove the predictor with the largest VIF. If it exceeds some threshold, for example 10, it exceeds say 10, and then we take it out, and then you fit the model again, calculate the new VIS with one less variable, and then we continue until we don't have any more seriously multicollinear variables in the model. Okay? And so we repeat and then repeat until no more multicollinearity. Okay, so that's the basic idea, and so I do want to illustrate this numerically. So I'm going to head over to the computer and do another our demo for you. So I'll get that set up and be right with you. Okay, so I'm going to run through two examples. Okay, so the first one is I'm going to revisit the coffee data that we used last class. Okay, so I'm going to load that in, and just to remind you of what's in here. Okay, so notice that we have, if you recall, we have one categorical predictor with the three categories for the three processing methods, and then we have a bunch of continuous variables. Okay, and then we're treating, in this case, we're treating flavor as the response. Okay, and so as I mentioned, we can look at to detect pairwise collinearity. We can look at two things: the correlation matrix, and we also look at the scatter plot matrix for all the pairs. Okay, so we can compute these in R as shown here. So we have the generic correlation command. So it can be used in terms of, like, you can put two vectors, right? So you put correlation of an x vector and a y vector, and it'll compute the correlation between them. But you can also put a matrix, and then it will compute all the correlation between the pairs, so all the pairs of columns in the matrix. We can do that, and as I noted here, this is not going to work out of the box because we have a column which is not numeric, and so R will complain about that. Okay, so so one way around that is we can we can just ignore for example, ignore the first column for now. So you can always use minus in the indexing to take out a column. So if you do, so remember it's indexed by row, comma, column. So we want to ignore the first column for this calculation. I can just do so use all the rows but take out the first column. Okay, so this will give me a correlation matrix. So this lists the correlation between each pair of variables in this matrix as indexed this way. So of course course, the diagonal is 1 because each variable is perfectly correlated with itself. And so, for example, the correlation between aroma and flavor is around like 0.73. Okay, so if we glance through these numbers, then we can already get a sense of whether, for example, there are any predictors that are strongly correlated with each other. So remember, we're treating flavor as the response. So some of these other correlations between the predictors would help us detect pairwise multicollinearity. So for example, aftertaste and aroma, if we put both of them in the model, for predicting flavor, we see that aroma and aftertaste are somewhat correlated amongst themselves, close to 0.7. And so you can see how the predictors are themselves related pairwise through this matrix. So in a similar way, we can so we've computed the correlation matrix. We can also look at this visually by plotting the pairs of pairwise all possible scatter plots between these columns. Okay, so I can do the same thing. So instead of core, I put pairs, and then I will produce scatter plot matrix of all possible scatter plots among these variables. Okay, so let's blow it up a bit so it's a bit larger. Okay, so if you look at these scatter plots, so it's interpreted the same way as you would for a correlation matrix. So the variables are labeled along the diagonal, which is a convenient way to put these labels because you wouldn't plot a variable with itself. Okay, so you can therefore see aroma and aftertaste have this scatter plot. Okay, so these are just so just like with correlation, these two are representing the same thing. Okay, so aroma and aftertaste has this plot and this plot. It's just a matter of flipping which one is on the x and y axis. Okay, so as we saw in the correlation, this one was about a 0.7. Okay, so plot this pairwise scatter plot matrix can give us some indication then of whether some of the predictors are strongly correlated amongst themselves. So this is a visual way to see it, whether there's any linear relationships are visible among pairs of variables. Okay, so another way to call the pairs command is to explicitly list which variables we want to plot. So we can use the formula syntax as well by putting the tilde sign, and then we just put plus signs between all the variables that we want to include in this pairwise scatterplot matrix. Okay, and so as you may have noticed, when we define the variance inflation factor, and then look at the interpretation in terms of r squared j, that assumes that we can fit multiple linear regression models for each of the x's in our data. So in this case, we'll run into a slight difficulty because we have a categorical variable, and so what we would need to do explicitly, for example, so that we can use this variance inflation factor framework, is we would instead fit the various indicators or dummy variables that the categorical variable would be decomposed into. Okay, so I showed you last time how we encode our own indicators, and so let's do it as follows here. So let's create a new variable for wet, and encode it to be 1 if the method is wet and 0 otherwise. Okay, so I'm gonna add this variable to the coffee data matrix, and then I'm also going to add our own indicator for semi-washed. So it's going to be 1 if the method is semi-washed, and then 0 otherwise. Okay, so we now have our indicators, and so now let's demonstrate how much variance inflation occurs for these particular variables. Okay, so based on the framework, we talked about using R squared for individual predictors. Well, first, let's fit the full model. Okay, so let's so this is the same model that we fitted last lecture, except now I'm going to explicitly just to make this a little easier, is I'm going to put these indicators that we've defined into the model instead of having R do it automatically using factor. Okay, but otherwise this is the same full model as before. So let's fit that. Okay, and so now we can calculate R squared from various regressions of individual x variables fitted on the remaining predictors. Okay, so in this, just to show it in full, I've done it as follows, so it's clear. I've taken the first variable, so that's wet, and I'm fitting the regression of wet on all the other predictors. So I've taken out the response and I moved the predictor, so I moved what was the predictor wet to be the response, and I'm fitting regression with everything else on it. Okay, so I'm going to fit that regression, and then I'm going to extract the value of R squared. So if you recall, we have the summary of the the summary of the regression. And you notice that as part of the summary output, R does give us the calculated value of R squared for the regression. And so we can actually extract the exact value of that by extracting the attribute R dot squared. So that's what I'm doing here. So without rounding, the R squared is this value which has been shown in the regression summary output. Okay, so according to the equivalent variance inflation factor formula, I can calculate the VIF for this particular predictor, 1 over 1 minus the R squared for this predictor. And so I have the value 1.236. So in other words, the interpretation is that in a regression with all the variables compared to a regression with just this one, the estimated variance has increased by a factor of a little 1.24. Okay, so which is not a very large inflation. In fact, it means that the variable wet is not very linearly correlated or dependent on the other predictors, which we have in the model, which is generally a good thing, because in fact, if based on the term we've talked about before, sometimes we have orthogonal columns. Okay, and so it's good from a modeling point of view for the columns of X to be as linearly independent as possible for the reasons we talked about, so the variances don't get too inflated as a result of including them in our model. Okay, so we can do the same type of calculation. So I'll just do a couple more. So in this next one, I'm treating aroma as the response, and then and fitting the regression with all the other predictors in it. And likewise, I calculate a variance inflation factor for aroma, which is probably going to be a bit higher because even based on the pairwise correlation and scatter plot, we see, for example, aroma is somewhat linearly related to aftertaste. Okay, so so we already know if we were to fit aroma and aftertaste, the value of R squared would be about 0.68 squared, and in fact the R squared goes up a little bit more when we fit aroma on all the other predictors as well. Okay, so in fact, that goes up to, we can look at this this value about 0.52. So that actually reminds us of something we talked about before. When we put more variables into a regression model, R-squared can only go up. So for example, we did aroma on aftertaste. The R-squared would be about maybe about 0.45 because it's the square of that correlation, and it turns out by adding all the other possible predictors, the R-squared goes up to about a 0.52, which corresponds to a variance inflation factor of about 2.1. Okay, so I can calculate some other ones in the same way. So the one for aftertaste is larger at about 3.45. Okay, so as we might imagine, there are functions and packages that can do all of this calculation for us automatically with just a single command. So there's a package called CAR, which does these, which has a VIF function. So I'm going to load the library. So just do library and then the name. So if you don't have it installed, then you would first want to install the library. So this next command tells you how to install the package in R. So you do install packages and then put the package name in quotes, and then that will install the package. And after you've installed it, then anytime you need to use it, you just call it. You can just load it up using the library command. So all I have to do here is to take the model I fitted, the full model, and then wrap it inside the VIF function, which is from this library, and then that will calculate all of the variance inflation factors for each of the P predictors. So this gives us a benefit of manually coding our indicators here, because then we can get a VIF for each variable separately, including the indicator or dummy variables for the categories. Okay, and then we can see that these numbers indeed match up with the ones that we calculated from these individual regressions. So, for example, aftertaste is about 3.45. Okay, and so now that we have all of these VIFs, we look at the numbers, and nothing really stands out as being very large. So in fact, 3.45 is indeed the largest one here. So we don't have any instances of serious multicollinearity. Okay, and so that means, if we remember, we did some f-tests for this model previously, and we removed a few of the predictors. So this in fact tells us that that we won't have any major concerns about the validity of these f-tests as a result of potential multicollinearity. Okay, so that's a good thing to be able to verify. Okay, as our second and final example, I'm going to load up the data for the pythons that I described to you earlier. And so there's a bunch of variables, and I extracted just a few of them for our purposes. Okay, so I'm going to post this data set on Learn after class. Okay, so I'm going to load it in and just show you what's in here. Okay, so the variables I talked about include the SVL, that's the snout to vent length, and then you have the mass of the python and also its length, and then the fat measurement. Also, as a predictor is the sex of the snake, so whether it's male or female. Okay, and so just so again for interpretability, let's just code up our own indicator variable. So let's just put a 1 for male and 0 for female. So I'll add that variable to the data matrix. Okay, and so one reason for doing that is now I can do, for example, the correlation matrix and also the scatter plot matrix using all of the using all the variables, and having coded male to be 1, then we don't have to go back and look at how R decided to code which one as 1 or 0. Okay, so let's do the correlation matrix for all of these variables, and then we can now throw away the first column because we've coded it as an indicator ourselves. So again, I'll remove the first column and calculate the correlation matrix between these 5 variables. Okay, and so it turns out, okay, if we're going to treat fat as the response, it turns out that, as mentioned, the three values, mass, length, and SVL, are quite correlated amongst themselves. So SVL and mass have a pairwise correlation of 0.88, and the snout event length and the overall length of the snake is very, very highly correlated, so over 0.99. Okay, and so I want to use this to illustrate what happens if we just fit a multiple linear regression with all of these variables. Okay, so the male or female of the snake, and then these 3 continuous predictors. But for completeness, first let's also make the pairs plot, so we can see how these pairwise correlations are visualized. And in fact, you can see the pairs matrix between SVL and length is almost a straight line. Okay, so that's where we get a correlation over 0.99, and so this, if we put both of them in the regression model, is going to exhibit a high degree of multicollinearity. Okay, so that's exactly what I'm going to do first to show what happens. Okay, so we will fit this model, and let's look at the summary of it. Okay, so based on what we've discussed, what's going to happen now that we know that we have 2 highly collinear variables? Well, the corresponding estimates of their variances, so in other words, the standard errors of the corresponding betas, is going to be highly inflated. Okay, so let's pay attention to those numbers as we look at the summary of this regression. Okay, so let's look at these. So here are the 4 rows for the predictors, and let's look at the standard errors and the t statistics. Okay, so it turns out, well, whether the snake is male or female is associated with fat, and the is negative. Okay, so that means on average, with all else being equal, males have a lower fat measurement. Okay, so that's significant. And likewise, the mass of the snake is highly significant. And now let's focus on the 2 variables which you know are strongly correlated, so SVL and length. Okay, so according to the estimates and the standard errors, the computed t-statistic, so in other words, the estimate divided by its standard error, is actually quite close to 0. Right? You have a minus 0.3 for SVL, and you have a 0.15 for length. So it looks like, according to, if we were to do individual t-tests based on this fitted model, it would appear that neither SVL nor length are significantly related to the response. Okay, so that would be, as it turns out, a misleading conclusion if we were to look at this and say that neither of these 2 variables are relevant for predicting the response. So in fact, let's go ahead and calculate the variance inflation factors to see how much larger these standard errors became, just simply because we threw in 2 highly correlated predictors into our model. Okay, so we'll calculate the VIF, and okay, so the one for male or female is pretty good. Mass is, as we expected, it will be at least moderately large, because we know that mass has a relatively strong correlation with length, for example. So it's not surprising this is 4.8. But then we have a massive variance inflation factor between the two length measurements because of their extremely high correlation. Okay, so according to our rule of thumb and according to our suggested procedure for eliminating, we can take the variable with the highest VIF, so that's length, so that's 1007, and let's remove that from the model. So since it has the highest VIF, so let's fit a second version of the model. Let's call it MPF2, and it has length removed from the model. Okay, so we'll fit it, and then we'll look at again the summary of it. Okay, so if we look at the for example, the t-statistics for the two original predictors, which is male, female, and mass, we notice that the t-values haven't changed all that much. Okay, so minus 4.1 and 22.2. So these haven't changed all that much. But now for with length removed from the model, it turns out that SVL has a significant t-statistic. And so what we find is this estimated standard error is much smaller now compared to what we had before. Okay, so we notice before the standard error was like 11 with an end, and the estimate was minus 3.4 roughly. So now that we have removed length, the estimates for SVL actually have changed dramatically, with the estimate which is now minus 1.6, and the standard error has gone down dramatically. It's about 0.76. Okay, so now that the very strong multicollinearity with the length variable has been removed, we actually get a very different conclusion. In fact, the p-value for SVL is now actually significant. It's below, at least at the 5% level, it's below 0.05. Okay, so this reinforces what we were talking about earlier, that the conclusions and hypothesis tests and confidence intervals for individual parameters can change dramatically when there is multicollinearity, and we can have incorrect conclusions. Okay, so now that collinearity is mostly resolved, so let's check. So let's calculate the VIFs, and now all the numbers. I mean, there is, as we already noted, there is moderately strong correlation between the mass and this length measurement, but well below what we stated as a useful rule of thumb of a 10. So all these are now well below 10. Okay, and so we can have a much more reliable estimate now of the true significance of this length measurement of Snellt event as a predictor for the fat content of the Python. Okay, so these two examples illustrate this idea that we were talking about, and you can see numerically, indeed, multicollinearity can strongly affect the estimates, and then we've talked about a simple way of detecting it and removing multicollinear variables from the model. So before we end for today, let me know in chat if you have any questions about what we've discussed. I'll also note that in general, what we're leading up to is what we call model selection or variable selection, and so this as we've done F-tests, we've done multicollinearity detection, and to really generalize this approach of figuring out which predictors to include in the model, we will be working up towards a variable selection algorithm. So often when we're dealing with very large prediction problems, we might have dozens of predictors, and so we'll need some sort of systematic way of deciding ultimately which ones to include in a regression model. Okay, so I don't see any questions in chat, so we'll pick up on the next topic. We're back on stream on Monday.